So, hello everyone. Also, a warm welcome from my side. I'm Noor from SimScale, and I am a product manager here responsible for our electromagnetics program right now. And today we'll be diving into something exciting: Joule heating predictions for electronic components. And here's the agenda for today. So first, a warm welcome from our side, and also a quick introduction to SimScale for the ones that are new to SimScale, especially. Then we'll be jumping into a live demo on the platform, and specifically, I'll be breaking down a Joule heating simulation on a battery pack model using cloud native CFD analysis. And then we'll wrap the session up with the summary of the results, and also we'll talk a few other crucial use cases for Joule heating. All right, so let's kick things off with a closer look at SimScale's capabilities. At SimScale, our mission is clear. It's all about helping engineers to innovate faster by making simulation truly accessible. So how do we do that? We do that by providing a 100% cloud native simulation platform. So that means you can access our simulation platform by using just your web browser. So there's no need for painful setups with remote access or where you need to go through tricky installations. And also there is no limit regards to simultaneous usage of your team or the number of simulations you like to run in parallel, and at the same time there's no limits when it comes to size of the models you want to run. And one thing I really like to mention is our real-time support in the platform, because when you have a question at any stage you are working on your project, you can click on support and directly reach out to our support engineers. So there is never waiting around for tickets to be checked, because our support team is dedicated to making sure they're solving your problems the moment you are raising those, the moment you're experiencing them, not a week later after submitting your question or ticket. So as you navigate through your projects, uh, you actually know that support is really a click away. And also, SimScale is a single platform where all of the physics are streamlined in an intuitive workflow. So you have flow analysis, structural analysis, thermal analysis, and the newest one, the last but not least, electromagnetic analysis, all in one single environment. So you don't need to switch platforms to use different analysis types, because it's all right here in one place. And you can seamlessly jump between these analysis types for the same model, but also for a variety of models, of course. So before jumping into the platform, I would like to first briefly talk about what is Joule heating and also why is that important. So Joule heating is a critical phenomenon, especially for during design of power electronics products and components. And it is representing the conversion of current passing through electrical conductor into thermal energy, and therefore resulting in heating. So as temperature rises in the conductor material, it can of course impact the overall efficiency of the components, and as a result, the whole design. That's why to enable engineers to perform Joule heating simulations, which is important, especially for power electronics designs, SimScale has launched new capabilities around this topic, and so that engineers can keep these temperature increases under control. All right, so now we can dive into a real case study. So I will be stepping out of presentation mode, and as you can see, I'm just switching between my browser tabs. So I'm still in my internet browser. I'm still using my same computer. I have an internet connection, and that's all. I don't have any high-tech gear with me. And now I will be going into my Joule heating webinar folder where my project for today is located at. So okay, now my model for today is already here. And what will we be investigating today is thermal behavior of this battery pack, where we are also taking the electrical conditions and therefore the Joule heating effects into account. Okay, so step one, usually in any simulation process, is to bring your CAD model. And to SimScale, you can actually bring your models from any CAD tool that you're comfortable with. But today I will be using our Onshape plugin to import my battery pack model, just to stay fully in the cloud. Yeah, we can see two of my design iterations that I will be covering up today are already here, but just for this demonstration, I will be importing one of those. And okay, while this is loading in a few seconds, what we'll like to see in the end is a result like this. So this is the post-processing state we are aiming for. So here, what we are visualizing is temperature distribution within this battery pack, where I can easily see and easily focus on inner components, and then yeah, really check where are my high temperature components are located as, and then after that, how can I iterate my design to improve my cooling efficiency and improve my cooling strategy. So that's the goal of today. And yeah, right now my CAD is already imported here as well. And as a next step for most of the CFD analysis, and another common state is to create a flow region, because right now all I have is the solid parts. And I would like to also consider my fluid flow. And before, without leaving SimScale, actually, you can also create this flow region very easily. Depending on your application, it can be both an external flow region or an internal one. And in this case, an internal flow region was generated, and it is already readily available in the platform. So I won't be doing that again. And yeah, next step is basically going into the simulation tree, and Joule heating generation is could be considered within conjugate heat transfer right now. So selecting one of these two CHD analysis types options is the next step to do. And yeah, actually, I created this setup project, which is missing some parts to fill together with you right now. So I will be following up this project I prepared here. So when we click on project title here, what we can see is there are some definitions given, whether to be considered within the simulation or not. So by toggling them on or off, you can decide on whether you like to take those into account or not. And today our application is focusing on Joule heating, so that's why it is, of course, toggled on here. And then I won't be going through each and every material setup step, but just to demonstrate, here is my SimScale default material library. So now I would like to assign my flow region, and I am using the air given in the default library and selecting my flow regions from my list here. But I can also, of course, for example, create my own materials, which I did for my battery cells here. And then I can also create some organization-specific materials which are only available within my team, for example, only privately shared within my team. And here what I also did is I collected all these cells and saved those as a separate selection. So whenever I'm repeating this simulation, I am not reassigning 90 different parts again and again, but simply I'm selecting this as my saved selection. Okay, next step will be assigning my boundary conditions because materials are done as well. And okay, so now here I'm selecting these 6 faces belonging to my flow region. And I don't want to enter one single value here because my goal today is to also assess how flow rate values, the given flow rate range is affecting my maximum temperature within my battery pack. That's why instead I will be adding my flow rate values as a list so that when I click run the simulation button, instead of waiting for each of them to be finished, I will be starting all of these 3 simulations all at once in parallel. Pressure outlet boundary condition is relatively simpler, so I selected some phase and assign, so I will be skipping this as well. And here is my reference potential boundary condition defined as well, which will be assigned to this phase here. And as you can see, electric condition is selected as electric potential. And then for current outflow, I would like to select this phase here. And since this is a discharge scenario, for electric condition, current outflow is selected. And I will get into details of how this 20 amps was calculated back when I'm back in my slides again. Okay, actually now my simulation step is setup is done. And as I click simulation run, when I like to start it, one thing I will notice is instead of creating one single simulation, I'll see that I was starting an experiment where I have 4 simulations instead, and they all started all at once, and they're all running in parallel right now. So I don't need to wait for the previous simulation to be finished to start the next one because they are all running in parallel right now. And again, going back to my results here. So right now we are observing temperature distribution on our base model. And yeah, as I've talked a bit about this result, now we can observe where are the high temperature regions, whether I have any dead zones during my fleet flow within. I can also check for a current density distribution, for example, if there are any spikes or what kind of design change I can consider based on these results. And also, as expected, I can see in each row how electric potential is changing based on my assignments. Okay, now I want to go back to my slides to see the results and a bit more talking about those. So this is a simulation setup summary slide here. So today the case study was revolving around testing optimal cooling strategies. Because we'd like to handle temperature increases caused by the current flowing through the battery components. And it was a 1C scenario where 20 amps was drained from the module. And I'll delve into the details in next slide of how we arrived at this current value. But just so you know, this value was directly extracted from battery cells specifications. So that here we are aiming for a design that shows real life scenarios as close as possible. And after simulating the original model as the base setup, we would like to observe how the design changes, especially at the thin sections. So I started with very thin bus bars, and then since it was lacking some uniformity, I increased the bus bars a bit, and we'll check the results very soon. Okay, now the simulation setup. As I said, the cell properties are directly taken from a battery cell specification, and here the row or the value I like to focus on is it being a 1C scenario, and based on the distribution of the cells within the pack in series and parallel, 20 amps was calculated for this scenario. And also the voltage drop was validated by using simulation. And here on the first bus bar variant, where the bus bars were 0.5 millimeters, we can see the high current density regions. And to have a more uniform current density within the design, one of the alternatives is to increase the thickness of the bus bars. And as we can see from the post-processing state given on the right, actually that helped. And our second focus today was to create a parametric study for the velocity inlet boundary condition. So we created a flow rate study to observe how the cooling efficiency evolves with changes in the flow rate. So as we can see, when the flow rate was a bit below 0.25 liters per second, we had a wider area where we observed 37 degrees and higher within the battery pack, both within the battery cells and also on and around the bus bars. And when we increase the flow rate a bit above 0.3 liters per second, we saw that our cooling efficiency was a bit better in terms of reducing the high temperature areas within the pack. And after passing the 0.35 liters per second, actually we started to see the whole pack temperature being less than 37 degrees. And it was all these simulations were run at once in parallel. Okay, before we dive into the Q&A session, let's explore some other exciting use cases for Joule heating simulation, which are relevant for today's demo. So also, if you'd like to read more about these use cases in detail, please don't forget to go to the website by clicking this arrow on top. So then you will be able to read the whole blog post on this topic. So now let's start with the inverter design. Joule heating simulation can inform the users, the designers, engineers about temperature of electric components and the electric potential, also the magnitude of current density from the early stages of the design. And another relevant case is resistors, the power resistors, where the objective is to avoid subjecting components to prolonged high current loads. So simulation allows identification of locations where high current spikes exist. And through simulation, different cooling strategies can be easily assessed so that the design and the performance could be optimized. And lastly, let's talk about use case of the fuse block. And within fuse blocks, the goal is to protect sensitive equipment from high current values. So making the performance of the fuse is a top priority so that the sensitive equipment can be protected. And this is a prime example where Joule heating simulation comes into play because it allows us to observe the overload current around weak regions. And it's all about ensuring the fuse is doing its job effectively. Great. So now, actually, we covered all of the technical stuff for today. And we would really love you to bring your challenge to SimScale as next step. So obviously your application is our next challenge now. please get your team involved and get us involved. And you can simply get access by typing simscale.com or simulation.new in your browser. Or also you can directly reach out to us. We are happy to hear from you. And essentially, please remember that we are a click away to start simulating with SimScale.